Let's look at the graphs of some polar equations and check them for symmetry. First, we'll review the concept of polar coordinates. In the same way that an equation like y equals 5x describes the relationship between x and y on a Cartesian grid, a polar equation describes the relationship between r and theta on the polar grid. A point on the polar grid is represented as an ordered pair r, theta, where r is the length of a ray that starts at the origin and extends out to form an angle measuring theta counterclockwise from the polar axis. The graph of a polar equation can be symmetric with respect to the line theta equals pi over 2, which corresponds to the y-axis in rectangular coordinates, the polar axis, which corresponds to the positive x-axis, and/or the pole, which corresponds to the origin. Here, we see a graph that is symmetric with respect to the line theta equals pi over 2. To determine if the graph of a given equation will have this kind of symmetry, replace r with negative r and theta with negative theta, and see if the resulting equation is equivalent to the original one. There are two ways to test an equation to see if its graph is symmetric with respect to the polar axis. If replacing theta with negative theta results in an equivalent equation, the graph is symmetric. Also, if replacing r with negative r and theta with pi minus theta results in an equivalent equation, the graph is symmetric. If you replace r with negative r and the resulting equation can be rewritten as the original equation, then the graph of the equation is symmetric with respect to the pole. Let's look at another example. Use the symmetry test to decide what type or types of symmetry the graph of r equals 1 over 2 plus cosine theta has. We'll begin by testing for symmetry across the line theta equals pi over 2. Replacing r with negative r and theta with negative theta, we now have negative r equals 1 over 2 plus cosine negative theta. Recall that cosine is an even function, so cosine negative theta equals cosine theta. On the other hand, sine is an odd function, which means that the sine of negative theta equals negative sine theta. If we simplify cosine negative theta, the equation becomes negative r equals 1 over 2 plus cosine theta. The given equation has positive r alone on the left side of the equation, so we'll rewrite this equation to have the same layout. Multiplying both sides of the equation by negative 1, we get r equals negative 1 over 2 plus cosine theta. By the reflexive property, we know that r equals r. This means that 1 over 2 plus cosine theta should equal negative 1 over 2 plus cosine theta. But this will never happen, so the 1 over 2 plus cosine theta does not equal negative 1 over 2 plus cosine theta. Therefore, r equals 1 over 2 plus cosine theta fails the test and is not symmetric about the line theta equals pi over 2. Now let's look at another example. Let's check to see if r equals 1 over 2 plus cosine theta is symmetric about the polar axis. Remember, the curve is symmetric if replacing theta with negative theta in the given equation yields an equation that is similar to the original equation. Replacing theta with negative theta gives r equals 1 over 2 plus cosine negative theta. In the previous test, we saw cosine negative theta is equal to cosine theta. So, r equals 1 over 2 plus cosine theta. This is the original equation, so r equals 1 over 2 plus cosine theta is symmetric about the polar axis. The last type of symmetry is symmetry about the pole. We check this by replacing r with negative r and comparing the result to the original equation. When we make the replacement, we get something familiar. Negative r equals 1 over 2 plus cosine theta. We know that this is not equivalent to the original equation, so r equals 1 over 2 plus cosine theta fails the test and is not symmetric about the pole. Let's test another polar equation, r equals 4, for symmetry. Notice that there is no theta in the equation. This means that the equation is equal to 4 for all values of theta. The equation passes the test and is symmetric across the polar axis. Remember that the test for symmetry across the line theta equals pi over 2 is to replace r with negative r and theta with negative theta. Since there is no theta term, this test is just replacing r with negative r, which is the test to see if the equation is symmetric about the pole. Therefore, if replacing r with negative r yields an equivalent equation, the graph will be symmetric across the pole as well as the line. Now replace r with negative r. We have negative r equals 4. This does not look good. But remember that we have already shown that the equation r equals 4 is symmetric across the polar axis. There are two tests for that symmetry. We could either replace theta with negative theta, or we could replace r with negative r and theta with pi minus theta. Since we know the equation is symmetric about the polar axis using the first test, we know that the equation must also pass the second test. So, if we replace r with negative r and theta with pi minus theta, we will have an equation equivalent to r equals 4. Since there is still no theta in r equals 4, replacing r with negative r and theta with pi minus theta also gives negative r equals 4. This means that r equals negative 4 is equivalent to r equals 4. Therefore, replacing r with negative r gives an equation equivalent to the original equation. So r equals 4 passes the tests for the line theta equals pi over 2 and the pole.